Hello, welcome back to this lesson in algebra. Here we're going to talk about the so-called laws of exponents. So I know that you've all been exposed to almost everything that we're going to talk about in this lesson, but what we're going to do is we're going to put all of these laws of exponents in one place on the left-hand side of the board. It's all having to do with what happens when you multiply terms and divide terms that have exponents, right? And the reason that we're going to put it there and review it now is because in the next few lessons, we're going to be multiplying polynomials. That means the big terms with parentheses with lots of things in them that are added together. Once we multiply them together, it's going to end up with a lot of cross multiplication of terms and a lot of exponents to keep track of. So because we're going to be doing that in the next lesson, we want to learn and review the laws of exponents here. So what we'll do is I'll write them on the board without any proof right away. I'll go ahead and put them on there so you have them in one place. And then I want to go back through every one of them and really prove to you why they're true. Because I don't like, in general, just telling you, hey, trust me, these are the laws of exponents. I want to show you that these don't come from thin air. They actually make a lot of sense. And once you understand them a little bit and we get a lot of practice with using them, you won't even have to memorize them as an actual law because they'll just ultimately make sense when you start solving a lot of problems. So with that, I want to go ahead and write down what we call the laws of exponents. Laws of exponents. And what I'll probably do is I'll probably go ahead and leave this on the board for the next few lessons just to kind of have it as a review if we need to look back and kind of think about things. So again, I'm going to write them all down. There's only 5 of them. And then we'll talk about each one by one. So the first one is the following. If you have A, where A can be anything as we'll see, but it can be a number, it can be a variable, it doesn't have to be actually A, it represents anything, to the power of m, and you're multiplying that times A to the power of n. So what this means is you have the same base for the exponent, right? Or for the expression, but different exponents. So m and n are different. Then what you do is you use the same base in the answer and you add m plus n. This is something that you would see like in a textbook. So you add the exponents together in those cases. And we'll do a lot of examples, so don't stress out too much if it doesn't make a lot of sense. I just want to get them on the board. The next law of exponents is if I have a times b, where a and b could be variables, they could be numbers, but they're multiplied together inside here. And on the outside, I have the whole thing raised to a power called m. Then what ends up happening is this m kind of gets applied and distributed, for lack of a better word, to everything on the inside like this. A to the power of m times b to the power of m. So this one you may not have seen in a while, but basically if you have two things multiplied together with an exponent outside, then the exponent gets applied to each thing separately. Again, they're multiplied still, but each of the bases become raised to that power to that exponent. The third law of exponents is going to be a to the power of m, also raised to the power of n. So this would be like x squared raised to the third power. So m and n they're different exponents, but one thing is raised to a power, but then the whole thing is raised to the power again. What you have in this case is you have the same base, but you multiply these exponents together. So it's a to the power of m times n. All right? Again, we have to get through them to be able to explain them, so just bear with me if they don't make a lot of sense just yet. Then what if we have a fraction where the numerator of the fraction is a to the power of m and the bottom of the fraction is a to the power of n. So this would be something like x cubed and x squared on the bottom. Different exponents again. Then you end up using the same base and you subtract m minus n. Top exponent minus the bottom exponent is how you would simplify that. And then the final one that I'm going to have here, if you have a fraction a over b, again, a and b could be numbers, they could be variables, whatever. And on the outside, the entire fraction is raised to the power m. Then what you do is you distribute the m and apply it to the numerator, a to the power of m, and the denominator gets applied as well to the same exact power, so b to the power of m. So let me just double check. So we have m plus n, we have mn, we have mn, m minus n, and m and n like this. All right, so this is what we call the laws of exponents. There's actually probably one more that I'll say for a little bit later. We're not going to use it for a while, but these are certainly the most common things that you're going to run up against. So what I want to do now is, I don't blame you at all if you look at those and say, whoa, I don't understand those. Because if you're anything like me, I need to see some examples. I need to see like a concrete example to understand what any of this means. So this, as I've written it, is probably pretty close to what you would see in your textbook, or in your class notes or whatever. This is how math books kind of generalize everything. So they're not going to write anything with numbers. They're going to write it with A's and B's and M's and N's because it's general and it applies to everything. But what I want to do is go down each one of these laws and show you specific examples. I'm going to show you an example with numbers, and I'll also show you an example with some variables. And so the idea is not to be an expert at the end of this, but to at least understand all of these laws. So when we get to the next lesson, multiplying polynomials, you'll know which of these laws apply, and it'll just become second nature after a while because you'll be using them so much. So this is kind of like learning the alphabet, you know, this is the basic stuff that you're going to use for every problem. All right, so let's go over to the other board and we'll take a look at the very first one. I'll rewrite it on the board again over here. And the very first law that we wrote down was a to the power of m times a to the power of n. And we said that it was equal to a m plus n. So what I want to do is show you a couple of different examples. The first one I'm going to show you is in terms of numbers. What this means is that the base here, whatever it is, has to be the same thing. That's why they're both a. So let's just pick a number. We can pick anything we want. Let's pick 3. So a could be 3. So we'll pick a number, and we'll have to have an exponent in each case, but m and n are different, right? So let's pick whatever. We can pick anything. But let's say m is equal to 2, so we'll have 3 squared, and we're going to multiply it by, it's got to be the same base because they're both a, and I can pick a different exponent. It doesn't matter. For this example, I'll pick 3. So I want you to first of all realize that this example I'm writing down is a direct example that fits into this bucket. It's a base to the power of an exponent times the same base to a totally different exponent. I could pick different bases as long as they're the same, and I could pick different exponents as long as they're different. But for this, I'm just making something easy. And what we're saying is that the answer should be, well, let's look at it this way. What would happen if we did this by hand? What is 3 squared? It's 3 times 3. And then it's multiplied by all of this, which is 3 to the third, which is 3 times 3 times 3. So we've just blown it all out. What do we have in this case? Now we have 3 times 3 times 3 times 3 times 3, which is 3 to the what power? 3 to the 5th power. That's what this is equal to, right? Which, if you notice, is exactly equal to the 3 to the 2 plus 5. We said what's going to happen is you're going to add these exponents, 2 plus 3, here. So this actually checks out. I'm trying to show you with a numerical example that if you take something that fits into this category, and if you add the exponents together, you would get 3 to the 5th power. That's what this is telling you. You keep the same base at the end, but you raise it to the sum of these two powers. So 3 to the 5th. And the reason why is why? Because this is itself multiplied 2 times. This is itself multiplied 3 times. And since they're all multiplied, then you would just have 3 to the 5th power, which is the same as adding them together. So I hope you can see why this rule actually works. Now let's take a more of an algebraic example next. Another example would be x to the 7th power times x to the 2nd power. Now we've been doing this kind of thing a lot, but you can think of this as x times x times x times x times x times x times x. That's 7x's multiplied times x times x. So what's going to happen is you have all these x's multiplied together. What's going to happen is you're going to add them together, x to the 9th power. So 7 plus 2, exactly what the rule tells us to do. What if you have y to the power of 6 times y to the power of 2? All you have to do is check the bases are the same, correct? The exponents are different. All I do is add the exponents together, y to the 8th power. And the reason why is because this thing, if you blow it out, is y times y times y times y times y times y. That's 6 of them times y times y. So when you string them all together, there's actually 8 of them. And that's why this rule works. So I know we've used this rule over and over again already. You already know this rule. But I still want to put everything in one location to make sure everybody's on the same page with me so that when we get to the next lesson, nobody is lost. When you have same base, different exponents, you multiply them, you just add the exponents. That's all you have to do. All right, the next one that we had, the next rule that we had over there on the board is a times b inside of a parentheses raised to the m power, and we said that it was a to the m times b to the m. The way I like to think of this is when you have two things multiplied together in here, and they're raised to a common power. This power is almost like distributed, kind of like when you have something in front of a parentheses, it goes and applies to every term, right? This is kind of the same thing. The m gets applied as a power to the first thing, and then the m also gets applied as a power to the second thing. And no matter how many things you have multiplied in there, it gets distributed to each thing inside of there raised to the same power. So this is what the rule is. Now let's go and take a look at a numerical example, and then let's take a look at an algebra example. So let's use our nice friendly, let's say that a is equal to, in this case, let's change it a little bit. Let's say a is equal to 2, and b is equal to 3. When we have a and b here, all it means is that they're different things. A different number times a different number, or a different variable times a different variable, whereas in here, a was the same thing. So here we have, let's say 2 times 3, just to be something different or have something different, we'll raise it to the second power. All right? So if you were going to do this without using these laws, what would you do? You would say, well, 2 times 3 is 6, right? And 6 is raised to the second power. That's what I would get. But what we're saying is that this is exactly the same thing. So let's go down, I guess let's go down here. What we're saying is when you have two things multiplied raised to a power, we can apply that power to each thing individually. So this is also equal to 2 to the 2 power times 3 to the 2 power, right? That's what we're saying it is, right? And if we do this, then 2 squared is what? 2 times 2, right? And 3 squared is what? 3 times 3, right? So I can massage this a few different ways. I can say 2 times 2 times 3 times 3 is the same thing as 2 times 3 times this 2 times this 3. Make sure you understand this multiplied together is the same as this multiplied together. Why do I do it that way? Because I want to show you that this 2 times 3 is 6 times this 2 times 3 is 6, which is 6 squared, which is exactly what you would have gotten if you didn't even know about these laws. So I'm trying to show you with a numerical example, if you have two different things multiplied together on the inside and they're raised to a power, if you didn't even know about this with numbers, you would just multiply and say 6 squared. That's the answer, 36, right? But then I'm saying, hey, there's a more general thing here. When you're multiplying these things together and they have a power, then you distribute that power to each thing on the inside, which means 2 squared, 3 squared, and when you massage it all out, it comes out to exactly the same thing as 6 squared, which is what we got if we didn't even know about this rule. That's why I'm trying to show you the rule works. Now, it's pretty easy to see with numbers like this how it would work. Let's take a look at a couple of examples on how it would look with variable type of examples. What if you had x times y to the third power? You know, a lot of students will look at this and say, oh, it's easy, 6 squared, no big deal. Why do I have to learn this silly rule for that? Like, why would I ever do all of this? I agree with you. You would never do this stuff. I'm just showing you that they're equal. That's all I'm doing. Because when I come to this, then you have to know, what do I do? And when you have two things multiplied inside, that they're different like this, with an exponent on the outside, the exponent gets applied to each term on the inside. This is the final answer for something like that. So you see how if you didn't know this rule at all, you wouldn't know how to simplify this at all, even though it looks like I'm taking a detour and this is ridiculous to show you that this is the case. With numbers, I can kind of make it easy to understand, but when you get to the variables, you just have to know and follow the rule, which is what I'm proving to you is true. What if you had another one? Let's say you had y times z raised to the 7th power. So that's literally y times z times y times z times y times z, and on and on and on 7 times. What you would get is y raised to the 7th power times, whoops, not times y again, times z also raised to the 7th power. That's the final answer as far as expanding it all out. You can't combine these any further because they're different bases here. You can't add the exponents or anything because notice in order to add the exponents, the bases have to be the same. In other words, this first rule is basically telling you that the only way you can add the exponents is if the bases are the same. So the bases are different here. You can't add these exponents. You have to leave it alone. The bases are different here. You can't add these exponents. You have to leave it alone. However, this is a very slightly more simplified, expanded form than the other. All right, so here what we've done is we've taken a look at this one, which means you can add the exponents. We've taken a look at this one, which means that we can distribute an exponent in to each term. Now we're going to take a look at the third one. We'll go over there on another board, and we'll take a look at that. The actual rule, if I write it down again, it looks like this. A to the power of m, the whole thing raised to the nth power. And according to that rule that I wrote on the board there, that is equal to a times the product, m times n. So basically, when you have something raised to a power and then the whole thing is raised to another power, then all you do is multiply the exponents together, keep the same base. So let's take a look at a number example, and then let's take a look at an algebra example. So on the inside, let's say I'm using 3 a lot. So 3 to the power of 2, and I'm going to raise that to the power of 3. So if you didn't know anything about this rule, what would the answer be? Well, all you would do is you would say, well, what this means is 3 squared times 3 squared times 3 squared. Why? Because it's raised to the 3rd power. So whatever is in here gets multiplied by itself 3 times. All right? And then what you do next is you realize that, hey, these all have the same base. So just like that very first rule, when I have the same base and everything's multiplied, I can just add the exponents together, which is going to be 2 plus 2 plus 2, which is going to be 3 to the 6th power. And as you know, 6 is 2 times 3. So what I'm showing you in a roundabout way is that if I take something raised to a power and I raise it to another power, the answer that I get is the same base with the exponents just multiplied together. Because that's 3 to the 6th, which I'm just showing you by expanding it all out, is exactly the same as what you would get if you didn't even know about this rule. So the bottom line is not to ever do something like this with numbers. That wouldn't make sense. The bottom line is to show you that with numbers it's easy to understand why they're equivalent to one another. So anytime you have something with an exponent raised to another exponent, keep the same base, multiply the exponents. That's it. It's almost like it's distributed in and multiplied by the previous or by the other exponent. Now to drill it home, let's take a look at an example, an algebra example. Let's say we have x to the 4th power raised to the 3rd power. Now again, with this, I can play games with numbers and show you they're the same, but with this, how do you simplify? You have to know the rule. And the rule is power raised to a power, you multiply the powers. X to the 12th power. That's the final answer. All right? And again, it's because this is x to the 4th times x to the 4th times x to the 4th. That's what happens. And then you can add all the exponents together. That's why it becomes x to the 12th. Another example would be z squared raised to the 7th power. Power raised to a power, you keep the same base. 2 times 7 is 14. Again, why? Because it's z squared times z squared times z squared times z squared and on 7 times. So you add them all together, you get z to the 14th. And that's the final answer. We only have 2 more of these, and they're actually pretty similar, so it's going to go pretty fast. The next one is, what if we had a to the power of m over a to the power of n? And from the other page there, we said from our rules of exponents, it would be a to the top minus bottom exponent, m minus n, top minus the bottom exponent. Let's take a numerical example and see why that's the case. Let's say for the top, we have to have the same base. Notice we have to have the same base. So for the top, let's say we have 3 to the 4th power, and on the bottom it has to be the same base, but different exponents. So let's make it 3 squared. So this falls into the same bucket as this, same base, different exponents. What will it be? Let's say you didn't know this rule at all. What would the top be? It would 3 times 3 times 3 times 3. That's what 3 to the 4th means. On the bottom, it would be 3 times 3. But you all know that when you have things multiplied on the top and multiplied on the bottom, when you have the same common terms on the top and bottom, I can kind of cancel and divide out that 3 and that 3. And then this 3 will cancel and divide out with that 3. Why? Because I'm basically saying 3 divided by 3 is 1, and then this 3 divided by this 3 is 1, so it all disappears. So what I will have at the end of the day there is all that's left, 3 squared. That's all that's left, which, as you know, is 3 times 3, right? Which, as you know, is, another way I'll say it, instead of putting the 3 times 3 there, it's 3 squared, which is 4 minus 2. So I'm showing you with a numeric example that when you have something like this, the answer is 3 raised to the power of 4 minus 2, which is 3 squared. And the reason is because on the top, you're going to have a bunch of these things. On the bottom, you're going to have the same things, and some of them are going to cancel. That's why you subtract them, because everything that was on the bottom, all the 3's that were on the bottom will always cancel with what's on the top, leaving you with what's left over. That's why you subtract them like this. So another example, a numeric example would be, or an algebraic example would be something like x raised to the 7th power over x raised to the 3 power. So you don't have to do all this business. All you have to do is remember the rule. When you have same bases, different exponents in a fraction, it's x to the 7 minus 3, which is x to the 4th power. And the reason why is because on the numerator, it's x times x times x times x times x times x times x. That's 7 of them. And on the bottom, I'll have x times x times x. 3 of them will cancel because the 3 on the bottom will cancel with what's on the top, so I only have 4 left, right? Last example here, what if I had y to the 10th and y to the 4th? I don't need to do all the cancellation or whatever, I just say 10 minus 4. So it's 10 minus 4 in the exponent, which is y to the 6th power, because 4 of these will cancel with what's up here, leaving me with 6 left over. All right, so we've done every one of these rules of exponents, except for one. It's not hard to understand, so let's just take a look at that one, and then we'll be done, and we can start applying it. What if we have a fraction, a over b, where a and b are different, obviously, and I'm going to raise that whole thing to a power. First, let me draw your attention. What happened to the last time we had something in parentheses and a power on the outside? What happened was that power got applied to everything on the inside. In this case, they were multiplied together, so it was applied to each one of these terms. Now, what do you think would happen if we have a parentheses here and we have an exponent here? I mean, just based on what we saw before, you would guess that the m would be applied to the a, and then the m would also separately be applied to the b, and that's exactly what the rule says. It's going to be a to the mth power divided by b to the also to the mth power. All right? Because it kind of gets distributed into the top and the bottom. So let's take a look and see how this would work with a numeric example. Let's take a fraction, just a number, a fraction, doesn't matter what it is. Let's call it 3/5, and we're going to raise it to the power of 3. If you had no idea what this rule is, the way you would do this is you would say, okay, 3/5 times 3/5 times 3/5, because you know that exponents means you multiply times itself. But then you remember back from more basic math that when you multiply fractions, you don't care about denominators or common denominators or anything. All you do is you multiply the tops, and then you multiply the bottoms. So really what you'll have on the top is 3 times 3 times 3, and on the bottom you'll have 5 times 5 times 5. That's what happens when you multiply fractions. But then you'll realize that on the top, this is just going to be 3 raised to the 3 power, and on the bottom this will be 5 raised to the 3 power, just like this, which is exactly what the rule said you would have. The rule said if you had a fraction raised to a power, you would apply that same power to each part of the fraction separately, the numerator and denominator. So when you have 3/5 to the 3rd power, we've shown you that it's base to the 3rd, numerator to the 3rd, denominator to the 3rd, exactly what the rule says. Now again, you wouldn't really go through all this stuff. It's just showing you that this works, that it's the truth. But in reality, what you're going to see a lot more often is something like this. You'll have x over y, which is some kind of fraction, and you'll raise the whole thing to the 7th power. So you need to know, what do I do? Well, I take this exponent, I apply it to the top, I apply it to the bottom, which means x to the 7th, y to the 7th power. And that's the expanded form or the simplified form of this. Another example could be w over x, just two random variables I made up, to the 10th power. Well, I have a fraction raised to a 10th power, so it's going to be w to the 10th divided by x to the 10th. That's the final answer. So in this lesson, we've covered actually really important material, because these rules of exponents are going to be rules that you're going to have to use in every problem going forward. And the reason we review it now is because we'll be multiplying polynomials, and then later we'll be dividing polynomials. So you'll have lots and lots of powers, different powers of x, and you'll be multiplying or dividing by lots and lots of other powers of x. So we need to be really skillful and understand how to handle exponents more than when you had to do basic algebra. It's going to be more important because every problem we have will have this stuff. So we went through each one. The basic takeaways of it is, if you have two things multiplied together with the same base, you can add the exponents. If you have two things multiplied together that are raised to an exponent, you can basically distribute into the parentheses to each term that exponent. When you have a power raised to a power, you can of course distribute it in, but it has to be multiplied together. Notice that we said m times n here, and notice that this a really has an invisible power of 1. So really we kind of did this rule wrapped up in here, because m times 1 up here is m times the 1 that's on top of the b for the exponent gives you m. So the idea of multiplying the exponents is actually already wrapped up in this one, because these exponents are just 1. So 1 times m gives you this, 1 times m gives you that. But in any case, the general idea is when you raise a power to a power, you multiply the powers. When you have a power on the top and the bottom of a fraction with the same base, you just subtract the exponents. And then when you have a fraction, you apply the exponent to the top and to the bottom separately, which it really is the same thing as what you're doing here and also what you're doing here. So if I had to boil it down to 3 sentences, I would basically say the following thing. to try to remember. When you have two terms multiplied together with the same base, but different exponents, you can add the exponents together. And when you have things wrapped in parentheses, it could have powers, maybe it doesn't have powers, maybe it's a fraction, but the whole thing is raised to a power externally, then in general, that power is going to apply itself to everything on the inside, just like it gets applied to top and bottom here. It gets applied here with multiplication, it gets applied here. So some of these rules, even though they look separate, they're really kind of the same rule. And the good part about it, even though it's a little bit of a pain to learn it in the beginning, is we're going to do so many problems that you will never have to remember this list. Because after the first few, it'll just become like second nature. And that's my goal with it. So make sure you understand conceptually what it is. Follow me on to the next lesson. We'll start to multiply polynomials together. And you will be using all of these rules in almost every problem that we do.